Thanks, guys, for choosing this talk over Lightning Talks and over Travis. I hope you like it. It's my first time in Troopers. I'm enjoying the place very much, and I have to say it's one of the best conferences I've been to. Thanks to Eno and Nikki and all the guys. All right, so I'm here to talk about cryptography. There's usually like two kinds of bugs: the ones that you will find and fix before releasing, and the others that other people will find and probably exploit. And you want to minimize the amount of such bugs. So especially in cryptography, you can use the generic software tools for testing your software, but there's very few tools for testing, things specific to cryptography. So everyone has to test, okay. What I've seen is that there's very few papers or talks. Actually, I haven't seen no paper, no single talk about testing your cryptographic code. And yet everyone has to do it. Nobody talks about it, but everyone has to do it. When I see the open source projects, the crypto libraries, OpenSSL, Embed TLS, all those guys, what I see in industry is even scarier. It's really terrible. And the worst I've seen is in standardization, standardization consortiums. Sometimes they don't test anything at all. That's totally scary, and I thought I could help a bit by presenting my experience in this area. So why nobody talks about it? Maybe because it's hard. You need to know cryptography, and you need to know software, and you need to know software testing. So the methodologies, if you need, are not documented. You won't find them anywhere. You can just take the general software testing methodologies and try to apply them to crypto, but it will not always work. And the tools are not available. I don't know of any tool that's specific to crypto. Maybe one or two, but these are commercial ones. All right. So why I'm here to talk about this? So I wrote a couple of implementations, some few open source stuff, a lot of proprietary stuff. I reviewed a lot of code. I found many bugs. And sometimes I was in a situation where I had to write reference code for cryptography for stuff that could be deployed in million smart cards, for instance, and stuff that cannot be patched. So if you make a mistake, if you have a bug, it will be here to stay, and it can have some catastrophic impact. So I made many mistakes, and to prevent myself from doing such mistakes, I tested many tools, some good ones, some not so good ones, some methodologies, so that's what I'm going to talk about. So when you talk about testing, there's usually two things. You want to test functionality and security. Functional testing is basically making sure that the good input gives the right output, and making sure that the invalid inputs will trigger the appropriate response and will not crash the system and will fail gracefully. So you can see this as like testing all the execution paths of the system, all the possible ways to be right, all the possible ways to be wrong. So security testing is in the situation where you have an attacker and you want to prevent the program from being abused. So this is the algorithm and the compile code. You want to make sure that it doesn't leak secret, that there's no memory corruption, and all this stuff. In crypto, usually, this often overlaps with functional testing. Just to give you an example, for example, you want to test that if you use some block cipher in CBC mode, you want to check the padding. So functionally, you want to make sure that when the padding is correct, it's accepted, and when the padding is not correct, it's rejected. So that's fine. But depending on how you reject the padding and how you implement it, your code may or may not be vulnerable to padding or guard attacks. So functional correctness doesn't imply security of your code. So then what are we testing? There's two scenarios. Either you test code against code or code against specification, for which you have no reference code. And usually when it comes to crypto, you usually test C code because it's more efficient. And well, that doesn't help because, as you know, C code is it's very easy to have bugs. All this memory allocation and memory unsafety. So the first case, it's the easiest one. When you have reference code, you can generate as many test vectors as you want because you got the original source code, let's say. That happens typically when you want to port some, the C code to some other platform or to some other language. what you usually do, we are lazy, we'll assume that the reference code is correct, and many times we won't check the reference code against the specification. But from my experience, many times you will find bug in the reference code that you're given when trying to implement it. So you should make sure not to reproduce the bugs in the reference code in your own code. The second case is trickier. It's when you have the specs, you have the document. I don't know if it might be some academic paper, some standard document, and you have to convert this to C code or to whatever language. Sometimes you're lucky, you have test vectors, so a sequence of inputs and respective outputs, and sometimes you have nothing. I've seen this, it's totally scary in some pay TV standards where you just have the specs and no way to test your code, no test vectors. So, and on top of this, the specs can be incomplete or incorrect. Incomplete meaning that you have some scenarios for which you don't know whether or not it's valid or invalid. And if your gut feeling says, okay, it's invalid, but you're not told, how your program should react. So the best approach for this, and like what we're doing in our company, is to have two different people working independently and implementing the specs. It might be in the same language or different languages. Sometimes what we do have someone implementing it for software in C and someone for hardware in some HDL language. Okay. So Collier have this lazy Dante analogy, the 9 circles. It's the 9 levels of testing that you may want to implement, from the most basic to the least basic. You probably won't need all those tests, but just know that these exist. I'm telling you more what to do than how to do it, and I've probably missed many important points. So feel free to interrupt me or to talk to me after the talk. So the most basic one is just test vectors. You got some input and outputs. You want to check that this at least is correct. If you can choose what kind of inputs will be in your test vectors, you should make sure that you maximize the code coverage, that you choose inputs with many different lengths, many different values, so that you cover all the corner cases, for example, of your cipher. If you're testing like a block cipher or a hash function, you have this notion of block. And the problems usually happen when you don't have the size is not exactly a multiple of the block size. There's been many bugs in this situation. You want to test consistency, coherence, like the Brutus toolchain is doing. It means when you encrypt something, you want to make sure it decrypts back to the same cipher. This sounds straightforward, but I've seen many ciphers many implementations that did not make this check. For example, in the recent competition Caesar. And if you have many test vectors, like thousands of test vectors, and if you don't want to store everything, you can just store something that's like equivalent to a hash of all the test vectors and like all this checksum. That's what the software of DGB Supercop is doing. Just a simple example, we had a bug in our hash function Blake, was candidate for SHA-3, and the bug was pretty simple. You see the patch here, and nobody noticed it for 7 years, even NIST. NIST did many tests, they spent dozens of hours testing our code, but they didn't find this one. It was found while some user was reviewing the code carefully before implementing it in some critical system. And this is the case that I mentioned before, where you hash some blocks and you have a block of very specific length. And this is what Supercop is doing. So you see, he's testing a block cipher, but he's not just testing the test vectors, but whether or not the cipher is writing to the input, is writing before or after the output buffer, whether you get different ciphertexts in different settings. So he says many tests to do, not just whether or not do I get the correct test vector. So then the basic software hygiene, prevent all the memory corruption, memory leaks, the basic secure coding. But the problem is that cryptographers, usually they're not familiar with this kind of test. They don't know the tools, they don't know the secure coding practices, so you see many funny things. So make sure at least to use the standard static analyzers, Coverity, Prefast, all this stuff. There's many open source ones. Valgrind, DC long sanitizers, scan build, this kind of thing. You may even want to test to fuzz it at this point. What I'm saying this is extremely important. It's the most important testing that you will do as far as security is concerned. If you look at Heartbleed, at GoToFail, they were not purely cryptographic bugs, they were software bugs. Okay. Now that you've tested the basic software security, the basic functionality with test vectors, you want to test invalid use. So check that when you get a malformed input, an invalid value, you get the expected error. Okay. So like if you receive a length that is not within the bounds, obviously you should reject it. We've had this recently in the password hashing function Argon 2, so which we selected earlier this year. We're missing a check, and this was not in our test suite. We were only testing valid values of this parameter, and someone had a really good idea to test invalid values, and he found this one. Okay, so do what I said, don't do what I do. This one is hilarious. You have to take the optional features, not just the nominal case. And that happened in OpenSSL. So as you know, OpenSSL is usually full of bugs. They had behind an if-def, they were testing if the key used in the DES cipher, so the standard from the 70s that nobody should use today. There's a couple of weak keys, so keys that make the encryption function identical to the decryption function. It's not such a big deal, that's why they made it optional. So they made it optional behind an if-def, and apparently nobody used it in like 11 years. And the bug was here, you had 2 exclamation points instead of 2 bars. So it didn't even compile. So they didn't even try to compile it. And what OpenSSL did, they fixed the code, and they released an updated version. And LibreSSL, so which is a forked version of OpenSSL, well, obviously they removed the code because nobody cares. The fifth one is randomness. Cause, you know, if your randomness is broken, your crypto is broken, and you don't get no security at all. Difficulty is that it's usually hard to catch the bugs in random generators because, I mean, you can try to use statistical tests. They will find the most obvious problems, but they won't find the real problems hard to catch. So you should make some basic sanity checks, the statistical tests, make sure that if you reboot your system, you get different random values. If you get different devices, they also give you different random values. A classical bug is what happened in Debian. So again, this is ridiculous. I mean, Debian is a gigantic project with many, many contributors. And the story here, to make it short, is that some guy was compiling the PRNG in OpenSSL, and Valgrind raised a warning. And the guy noticed that if you removed a line of code, then the Valgrind warning disappeared as well. So he was not sure of what he was doing, so what did he do? He sent an email on the Debian developers mailing list, and he asked out, okay guys, what do you think? Should I remove or not this line? Is it safe? And only 2 people responded and said, well, go ahead, it looks okay. Well, what happened? He just removed almost all the entropy, almost all the security of Debian's PRNG. And he was left with like 15 bits of entropy, meaning that you had only approximately 32,000 different keys for OpenSSH if you generate keys with the generator. So it was a big failure. Timing leaks, if you care about this happens if the execution time somehow depends on your secret, meaning on the key or on the secret message. So you want to avoid operations that are not time constant, typically branchings, even things like insecure buffer memory comparisons. What I've seen is sometimes people think that, okay, the source code looks constant time, you know, there is no branching depending on any secret. But what may happen is that the compiler may want to be too smart, and he may turn your constant time source code into non-constant time assembly code. So make sure to also check the assembly. There's a nice tool to do it by Adam Langley. It's called ctgrind. It's a patch for Valgrind. will basically say that, all right, here's my secret value. You will poison some value, and then it will tell you whether or not a value depending on your secret enters an instruction that is not constant time. So basically, it will tell you whether or not your code is constant time, the compiled code, not just the source. Seventh step that I want to do is real fuzzing. I call it dumb fuzzing because dumb fuzzing is in the case where the fuzzer doesn't really know what kind of API it's fuzzing. It's just sending random data in a more or less smart way, but still he doesn't know what he's fuzzing. It may give some interesting results if you're fuzzing parsers, because parsers are usually full of bugs. Big number arithmetic, things like RSA or the operations underlying RSA or the Fehellman. There's a couple of CVs for bugs that were found using a fuzzer. I think it was AFL fuzz. And some guy using AFL also found bugs in our function argon too. What happens sometimes is that people rediscover bugs using fuzzers that other people have found manually. But I mean, it's the lazy way to find many cool bugs. But you should not, there's many cases where it's totally useless in crypto. Like you should not fuzz symmetric keys, you should not fuzz the values of messages encrypted in symmetric cipher because there's a single execution path. The more advanced approach is what we call smart fuzzing. So in this case, the fuzzer knows what kind of API, what kind of function it's fuzzing. So he knows in advance the type of input that are likely to trigger a bug. That's what the company CryptoSense in France is doing. I think they do it pretty well, but their software is just commercial, as far as I know. And it's usually more for higher level protocols than low level algorithms. And I think those guys, they use it to test compliance to the PKCS standard. 8, verification. So I don't know if some of you were at the Langsec talk before. That's about like having mathematical proofs that a program is correct. So correct meaning that you have a model in some language, and it will check that your source code exactly matches this model functionally. It will test functionally correctness, but not security. So it may find bugs that have some security implications, but the point of verification is initially not to test the security of your program. Unlike the Langsec approach, which is more general, so to speak. So if you're interested in this, you definitely want to check the crypto language by the company Galois. I don't know, they've worked on this for maybe 10 years. They did a really good job. They created a specific language, description language, in which you will specify your crypto, you will define the model, and from this specification, you can extract a C or Java or LLVM or VHDL code that is guaranteed to be equivalent, functionally equivalent to your initial model. And they also have a tool which, if I remember correctly, is open source, the SAW. It is doing the opposite. It takes the C code or the LLVM IR or the Java, and it's transforming this back to a model in crypto language. Some guys are even implemented TLS in such a way that it can be verified according to the TLS standard. So I don't exactly know how far they went, what is verified, what is not verified, but that's an amazing work, and I mean, you should check it out. And the Langsec party, you can talk to Sergey or Jake, who are here today. The last part and the most advanced one, so if you're in a case where, for example, you have high value assets on smart cards, on FPGAs, and any embedded device, in game consoles, you want to make physical testing, test the security against real physical adversaries who may use side channel analysis, like electromagnetic analysis, laser injection, glitching, all these techniques, even fib. So that's what we're doing in our company. This is pictures of our labs. We have all this crazy equipment. What's a bit depressing is that at some point you can break everything sometimes. The question is just how much it costs, which level of skills, how much time. but then it gives you a pretty good idea of how secure is your system. Okay, that's already the end of my talk. So I hope I gave you a quick introduction of the different types of tests for your crypto. Maybe a small disclaimer. So you know the Pareto principle that you get 80% of results with 20% of the effort. I think it somehow applies to the case of crypto testing and maybe of software testing more generally. I mean, the most time you will spend, the fewer bugs you will find. So maybe your manager will tell you, okay, you can stop here, you're wasting your time. Because you will find less and less bugs the more time you spend. But maybe after some time, you will find a really high value, a really critical bug that will make all the effort worth it. So it really depends on, you know, prioritizing your tasks, the value of what you're predicting. And I mean, at the beginning, you have test vectors and basic software tests. And here, maybe you have fuzzing and verification and the other stuff. Okay. And so another point I want to make is, I mean, don't rush directly. Don't start using the advanced fuzzers or the verification. Start by using maybe the simple test, dumb fuzzing. You will find many bugs, and it will take much less time than the guy who is doing some crazy, using some crazy techniques. Actually, I use one of those automated tests, this one by CryptoSense, and apparently there's some cryptographic problem on one of the DNS servers of ER&W. So they probably know it, but they use an insecure Diffie-Hellman parameter. Maybe I should report this. So yeah, bottom line, start by doing, just be lazy, start by doing the automated tests, the free stuff. You can outsource this to an intern on whatever. But yeah, keep in mind that this will not replace a skilled reviewer. Problem is that there's I know very few people capable of doing this, like people who will find bugs in implementations of elliptic curves. It takes a really lot of work. There's a couple of companies who are doing this, but it's really tough. So to save some time, to make the job of those guys easier, to make the tools more efficient, make your code. I mean, if you follow the talk of Jacob before, yeah, make your code as simple as possible. Avoid pointers of pointers of pointers of pointers. This is one of the reasons why Heartbleed was not detected by static analyzers, because the reference level was too high at some point. So maybe it takes some time at the beginning, but this will be worth it. You can check out the rules on our website, cryptocoding.net. We have a couple of best practices. So don't like the word, but it's a wiki. You can contribute new recommendations. And well, thank you for attention. I'm happy to take questions or later tonight. Thank you.
Yeah, thank you very, very much for this short but very interesting talk. Are there any questions left? Yeah.
Always wondered what are the real reasons today to rely on C code. I know there are some issues with some garbage collecting languages like Go or Java, but is there really no alternative? Or do you think that the new evolving languages can?
Well, speed, simply. Usually you want to use like the low-level instructions to make your function as fast as possible. And usually you don't have bindings for the intrinsics, for example, for the SIMD instructions. These are not available in Python or Go, or it's difficult to use assembly in these languages. So I don't really know of any implementation in higher level language that is as near as fast as the C code. I don't know the numbers. I've seen some people implementing stuff natively in Rust, but in terms of speed, yeah, I don't know how competitive it's with the C. But usually people first write some C code and that other people do some bindings on or wrappers around it. It depends. Sometimes it doesn't matter, but if you talk to folks like at Google or this kind of place, a simple cycle per byte, it really matters for them. And if you take the case of AES, some people there are telling me that the AES with native instruction is still kind of too slow. I mean, they could use faster cipher.
Other questions? Okay, then thanks, Jean-Philippe.
Thank you, guys.